You're muted.
Okay. Hi. Thank you. Thank you for explaining. I didn't see that. So this is the first question. Clock frequency and clock period are essentially inversely related. So frequency is inverse of the clock period, and clock period is inverse of the frequency. So it's essentially f equals 1 by t. And as you can see, the frequency, if it is 4 nanosecond, then we can just put that number here, for example, 1 by 4 nanosecond, and that would be maybe 0.25 gigahertz, right? So that's the frequency. Wow, my handwriting is really bad. So I hope you can understand this, right? So let me write it. So if I write 1 by 4 nanosecond, that would be 0.25, and nano is inverse giga, and then second inverse is hertz. That's it. So you can use the same for other equation and find out the value for it. I hope everyone is on the same page about this. Let's go to the next question. Convert the following hexadecimal number to decimal. I guess very simple stuff that we can do is get these digits and then multiply them with the value of their position. So for example, if we take this number, then 1 times 16 squared plus 0 times 16 1, that is 16, and then f, or 15 times 16 to the power 0, that is 1. So we will have 16 squared is, I guess, 256. Is that correct? Yes. 16, 160, and then, yeah, I guess so. And then we have 0, and then we have 15. So that's the number you will have for 105 in decimal. Same way I can do the next part for E5. I hope that's easy. At any time, if you have any questions, any confusion regarding any of the problems, just let me know. I'll try to resolve that. Okay. Next part, we have to do algebraic manipulation to convert the following equation to sum of product. So there are different stuff that we have to do. First of all, to convert to sum of product form, you need to have all the literals. So what are the literals? Literals are A, B, and C. So in that case, if you have to convert the first term, for example, if you want to convert this A plus B and A naught plus AC times C, you have to make sure that all the terms have at least one of these literals. So it will have, for example, if we take this A plus B, A naught plus AC B, then we need to make sure that all the terms have A, B, C, some form of A, B, C. So let's do this. If I expand it, there would be A naught, and then B A naught, and then AC plus ABC, and then all. Okay. So A naught is 0 because the same number like A naught, B naught, C naught, that should be 0 added together. One of them would be 0, so 0 and whatever is 0. Then we have A naught B, and we have AC plus ABC multiplied by B. So this is the 4. And then from here we will have A naught B plus ABC plus ABC. So here we have two terms essentially. Another one is A naught B plus ABC. However, this term is not in the correct form because we have to convert it to sum of product form. So it has to be A naught B, C plus C naught plus ABC. So we will have A naught B, C plus A naught B, C naught plus ABC. Now this is a proper sum of products form. We can convert it to gate level circuit. So we will have three lines A, B, C, and then the nodes, and then we will or have three AND gates, one for 1, 2, 3 line, and then we will have OR gates, like I guess three OR gates for these AND gates. Do you want me to draw the circuit, or do you think this is trivial?
I have a quick question, real quick.
Yes.
What would you call the most simplified version?
What most simplified version?
Yeah, so like the A naught B plus ABC. Is there like a certain term for the most simplified version, or is it just
I'm not sure. There might be, but I'm not sure what is the exact name of the most signified version. Most
cool?
simplified version. Yeah, I'm not sure. But it's you have to convert it to sum of products form. That's why you cannot use this form. You have to use this where all the three literals are present like this.
Could I do the sum of products form by setting it equal to the summation of m with 2, 3, and 7 in parentheses?
Which one?
Could I, instead of writing out a prime bc plus a prime bc prime plus abc, could I do like f in parentheses abc equals the summation of m for like the midterm, and then just put 2, 3, and 7 denoting that it's the midterm 2, 3, and 7?
Yeah, you can definitely do that. You can change the representation to some different representation like you mentioned, like with numbers, but you can also represent it this way.
Okay, thank
So
you.
since you have to derive it, like you have to derive the numbers, and by the numbers it can be different, and you just have to do one extra level of calculation for that, right?
Yeah,
So it's easier if you don't do that, right? So yeah. Okay.
okay. So it just saves me a step not having to do it.
Okay, so if I want to draw the circuit, like let me just quickly draw this. Yeah, you don't have to show the number, like what is the exact number. The mean term is with ABC is fine. So let's just draw the circuit from here. So we have A, and then we have A naught. Should be A. B. Since this is mean term, so we will probably need all of them. So I'll just use not get quickly. So this is A, B naught, A, B, C, and then there are not gates. So A naught, B, C should have A naught and gate, B and gate, and C. Is that okay? And then we will have another AND gate with A naught, B, C naught. So we should have something like this: A naught, A naught, and then we will have B, and then we'll have C naught. And then finally we have A, B, and C. So from here we will have A, probably B, and C. So these three gates will represent three terms, and then from here we will have the OR gate, because this is the sum of products. Tyler asked whether there will be enough space. Yes, there will be enough space to solve all of this. Yes. Okay, so we can convert this directly. I guess this is the basic form of the circuit, and then let me get rid of the circuit for now. Okay. Let me maybe open the solution I already have, so easier for you to kind of. Great. Okay. So this is the circuit here, and then the behavior of the D flip flop, right? So the question was, let me clear this. So we have a leader follower flip flop that has only one input D, and then a clock is inverted to the first flip flop, and then the normal flip flop here. So how can you trace the behavior if initially all the values you're assuming zero? So to complete the timing diagram, assume logic gets left tiny but non-zero delay. So we know that if we want to draw a timing diagram, it should look like, ideally it should like something like this. So we need to first draw our clock signals. So I've used Logisim to draw this, but you are not allowed to do that in your exam. So you have to draw these clock signals by yourself. And when you draw these clock signals, you need to change your input to something like this. For example, when you change the input from 0 to 1, and this is your input D, and then I have traced both QM, Q dash, and Q. So you will be able to see that is QM, Q, and Q naught. So when D is changed on the next rising edge, we should also see the this one should be corresponding to the Q, because Q is activated, like Q is activated at the rising edge. Remember that because of this circuit, QM is activated at the falling edge. So because it has a NOT gate here, so this one, because of this one, this falling inverter gate, we have the QM activated on falling edge. That's what's happening here. So because of that, we have QM activated on the falling edge. When we changed it, the edge was falling and QM got activated to 1. And based on QM, Q should get activated at the next rising edge, which is what we are seeing here. QM is the input to the next D flip-flop or D latch, however you call it. And then because of this D latch is updated on the rising edge, see the clock is on the positive. So the rising edge, the clock will change this, and then Q will be updated. At the same time, Q naught will also be updated. So that's what's happening here. Q is becoming 1 and Q naught is becoming 0. At the same time, if we change 0 here, for example, we change the input D to 0. Since this is on falling edge, QM is also being changed to 0. And on the next rising edge here, if I draw this line, next rising edge, like at the next rising edge here, you will see the output is changing to 0 for Q, because now we have changed the input to 0. So this is just the discussion that about timing diagram. So following this, you can draw the timing diagram. So for drawing the timing diagram, the strategy should be just write 0 1 0 1 0 1 like a clock cycle like this, and following the clock cycles, try to find the rising edge for the clocks which have connection to like this. Like here, the rising edge should activate this latch, falling edge should activate this latch. So if your circuit requires a rising edge, update your circuit states or flip-flop states at that time. If your circuit requires a falling edge, update your circuit's data on that edge. Is that clear? Any questions about this? How to draw the timing diagram? If not, then we will move to the next part, because there would be certainly some questions from timing diagram. So Jackery said you have still some kind of trouble. So what is the trouble? Can you share? What exactly, what do we want to know about it? So whenever you want to draw a timing diagram, first draw the clock cycle. Just draw the clock cycle like this. And then draw your, like this is the clock cycle. And then based on this, you should decide your input first. So your input can be 0, your input can be 1, whatever you want, based on number of inputs you have, number of signals you have. And based on that, you need to decide what is your output should be. So since this clock, you put random input. Yes, we can put random input, but we need to make sure that all the inputs are given. So all the inputs are covered. So if nothing is mentioned, then your input should cover all the cases. If anything is mentioned, for example, you might have some specific inputs. So in that case, you have to have those inputs. If you do not have, if the question do not give a specified input cases, then you have to cover all the input cases. For example, here it doesn't mention anything about the input cases, so we have to make sure that it covers all the possible input cases or all the possible output cases. Is that okay? Okay, next part is what is the recommended D input that would cover all the cases. So it depends on how many flip-flops you have, how many latches you have in your flip-flop, or what is the design scenario. So in general, we need to see the transition from 0 to 1 and 1 to 0. For example, here you can see the transition from when you give input 1, the output goes to 1. When you give input 0, the output goes to 0, something like this. So we need to see the transitions. That's what we want to see from your timing diagram. So if you can do it correctly, you should be fine. Okay. So moving to the, okay. QM is directly in sync with D, and Q are not lagged by the clock cycle. Q and Q naught are lagged by the clock cycle. Zachary, that's not exactly the correct idea, because they are like dependent on the clock cycle. So depending on the rising edge. So what you can see here, this graph. So let me show you once again, maybe. So follow this example, try to trace the rising edge and the falling edges. So rising edge and falling edge, this should give you some idea. So when we have a rising edge, if there is a change in the input, that should be reflected in the output of, in this particular circuit, output of the clock that takes the rising edge. So the follower or the servant is mentioned here, that latch flip-flop, which is Q or Q naught, that should be updated only at the rising. So coming back here, at the rising edge, like here or here, we will see update of the Q and Q naught. So Q and Q naught is updated only on the rising edge. Similarly, at the falling edge, like we have here or we have here, we'll see update on the QM. Why? Because the clock here in the latch, the clock is inverted. So this latch will get updated only at the falling edge. Is that clear? Okay. You're welcome. So we'll move on to the next part. If you have any other questions about timing diagram, please feel free to ask. If not, we'll move to the next question.
Can you just explain how do you know if it's a low edge or a high edge again?
So usually we consider all the circuits to have a rising edge transition. That's the general assumption. But here, as you can see in this particular scenario, the master, it has an inverted clock, and the servant follower has a regular clock. So if it's regular clock, that means we have a rising edge transition, right? An inverted clock should have a falling edge transition. Any other question? In the timing diagram? Okay, so probably I'll move on to the next question. Question number 4. I think that's not part of the syllabus or something. I think that's mentioned. Someone mentioned that. So let's not go there. Design something, like design whatever. Whenever we ask you to design something, it would be better for you to come up with the truth table or state diagram or transition table, whatever for that, and then design from there. If you can simplify it using K-map, that's good. If you cannot, that's also fine. But state table, transition diagram, state diagram, whatever you call it, that would be essential for designing anything. So you should not design just from your head, because that will make everything very complicated. We think in a different way, and after maybe 5 minutes, we'll think in a very different perspective and we will lose the connection. So it would always be better to get some state table or transition table. So what is the 1 into 4 demarks? 1 into 4 demarks means we have 1 input and 4 output. So based on the selector bit, we should select only one of the outputs, and that output would be given from the input. So it's something like this. So we will have some marks 1 2 3 4 output, 1 input, and since there are 4 outputs, so we will need 2 selector pins. So we have 1 input, 4 output, and then 2 selector pins. That's it. So if selectors are 0 0, then the output 0 would be selected. If selectors are 0 1, then output 1 2 3, something like this. So I've already uploaded the circuit here. it's again done on Logisim, so you can think about it. Since we have four options, so these are four lines, and then we have y0, y1, y2, y3. These are outputs, and only I0 is the input that we have. So that's the one input for the demultiplexer, and then we have four outputs. So based on this, we should see the output working properly. So maybe I can show you this one. So this is the circuit. So as you can see, if I select 1, 1, then output 3 would be selected. If I select 1, 0, 1, then output 1 would be selected. If I select 0, 1, then output 2 would be selected. And that's how it's all over. So if I select 0, 0, output 0 will be selected. So if what is the output? The output should be whatever we have here. So I0 is the output. As you can see, Y0, that's 1. And now if I do 0, 1, this one should be 1. If I do 1, 0, this one should be 1. And if I do 1, 1, this should be 1. That's how it's supposed to be. So this is the 1x4 demultiplexer. So let's. Okay. So next part. Yes. Any questions?
Can you maybe do a truth table for that question?
Truth table for multiplexer?
Yes.
Okay. Okay, so let's do the truth table here, maybe. So we have one input like I, whatever that is, and then we have S0, S1. So these are three inputs, and then we have our outputs, like four outputs. So Y0, Y1, Y2, Y3. So if you have input 0, selector 0, everything 0, then the output should be at Y0. Everything else should be like, you don't have to do anything, just 0, that should be fine. If you do I0, 0, 1, then essentially everything should be 0 again, right? So you can reduce this number of lines, and by writing, like if you don't want to write all those lines, you can just do 0. If I is 0, then you don't even have to care about anything. It should always be 0. Is that okay? Do you understand this part? So I can just get rid of this. Like instead of writing all this, I can just write 1, and that will cover all the I0 cases. So the next part is, if I equals 1, this is 0, 0, then Y0 would be 0. Y0 would be 1, everything else would be 0. Again, if I0 is 1, I is 1, and then 0, 1, this would be 1, 0, 0. From here, if it's 1, 0, this is 0, 0, 1, 0, and then 1, 1, 1. This would be 0, 0, 0, 1. That's the truth table. Is that okay? Any questions? Is I enable here? No, I is the input. I is the input here. Okay, so that's how you design the truth table, and from this truth table you'll have the circuit. So these are the inputs, I, S0, S1, and then we have the output for the four output. So move this now. Next question. Draw a state diagram. 1 cross 4, yes, 1 cross 4 is one input from the four possible output cases. So we decide which one we want to edit, and then we select that one. That's it. So draw a state diagram or an FSM finite state machine with no inputs and 3 outputs, XYZ. XYZ should always exhibit the following sequence, blah, blah, blah. The output should change only on a rising clock age. So that's a good information. make 000 the initial state and implement the controller using a state register and logic gates. So you can implement this using a state register and logic gates. So essentially you can implement this using D flip-flops, you can implement this using something. So what we have here, we have to use this kind of information, like we have to use the information that is given in the current state and to the next state and compare each of the bits as the next state. So essentially if we have XYZ, then we should at least need a 3-bit register so to identify the input. So for example, if we consider the current state 000, at the next rising state it should be 001. If it is 001, at the next state it should be 010, so on and so forth. So if we consider this state table, the state diagram would be very simple. Like you have 000. From there, the next clock cycle, you should be like, if I draw the state diagram from 000, and the next clock cycle, we should be at 001. The next clock cycle, we should be at 101 or 010. And the next clock cycle, we should be at 101. The next clock cycle, we should be at again 000. So that's a state diagram. There are no other transitions or anything. So it's just one clock cycle and we go there. That's it. So how can we decide what is the input for the flip-flops or whatever the register we have? So in this register, since there are 3 bits of information, 000, 001, so we can see 3 bits. So we need at least 3-bit register or 3 D flip-flops essentially. So using 3D flip-flops, we can implement this and we might need some gates. For example, for this to work, we need to know what is the next output given some XYZ. So let's consider this part of the table only. So we have 3 inputs XYZ, and from the previous inputs, we need to get the next bit of X. So how can we get that? So in this case, we have 1 only when a certain combination of XYZ is there, right? So if X is 0, Y is 1, Z is 0, only that case we have X equals 1. All the other cases, Y should be 0. So that's essentially X should be 0. That's essentially the information we want. And based on this information, we can set our D flip-flop. So if we have a D flip-flop that gives us the output of X, then this D flip-flop should have input from X0, Y00, then the input should be 0. 001, that input should be 0. 010, then the input should be 1. 101, again the input should be 0. So how can we get that? So we can get that using X bar. So let's say if we have a signal called X, we note that we get X0, 0, X0, and then if it's Y, so that's Y, and then we have Z0, so that's again not get Z0. So if we add these 3 together, then we get the signal for this line, which should be 1. So this is 1, and this is the input for D0. If this is not 1, then the input would be 0. So that's how you can get the input for X bit. Similar way, you can get the input for the Y bit. In similar way, you can get the input for the Z bit. So once you do that, your circuit should work properly, and it will go from 000 to 001 to 010, 0101. Any confusion, questions? How do you create the next state in the truth table for X? How do you know X is 1? Oh, because it's given, right? So I am assuming the first bit to be, it's given the first bit is X, second bit is Y, and third bit is Z. So this is the sequence. So we know from this, if there is a clock pulse, the next sequence should be this. The next clock pulse, the sequence would be this. And then next is this, right? So that's how we will have the solution. Is that okay? Okay. So let me show you if I have that implemented or not, I'm not sure. Okay, so if I just run this, it should be, let's do this. So 1, and then we have 010, 101, and then back to 000. Yeah, so very simple. X, Y, and Z, 3 bits have their own flip-flops. So essentially this is forming a register, and then we have this operation. So we can compare this with the register with 3 bits, 4 bits, whatever number of bits you want, and then implement the actual design. I'm showing only 3 bits flip-flop, so you can use a 4-bit register to implement this. Should be exactly same. If you do not have any questions about this, then we will probably move to the next question. Do you have any questions about this? Do we need to know a clock cycle is on rising edge in this problem? Yes, definitely. Because you can see we have some clock cycle input on all the flip-flops. So if the transition is on a different clock cycle, like if it's in a falling clock cycle, then we will need to use different thing, different implementation of the cycle. Any other questions? No, good. So we'll move to the next problem. Well, I see one question or no? No. Could you show us an implementation when it's a falling clock? We already have one implementation here, like one problem here. This one. In this problem, like the problem 3, we had both falling edge and rising edge transition. So for example, again, this transition is on the falling edge, like this transition that we can see here, it's on the falling edge, and this transition is on the rising edge. This transition is on the rising edge. So this is on the rising edge, this is on the falling edge. Because the clock is inverted, like this one has an inverted clock, this one has a regular clock. Then use not before clock, yes. If there is a not declared before clock for falling edge, yes. So we want falling edge, yes, yes. Everyone is correct. So the inverted clock cycle would get a falling edge transition. However, you might encounter in future some circuits that are by default using a falling edge transition or both edge transition. So that's not part of this syllabus for now. So we will assume that if you have a rising edge, it will be mentioned. If you need a falling edge, that will be mentioned. Okay, so that's for the first sample question, I guess. Let's move on to the next part. Convert the following decimal numbers to 8-bit to complement binary from blah, blah, blah. So this is very direct thing. So first you need to know what is 2's complement form. You can just directly get the 2's complement from any calculator or anything, but we have to convert it by yourself. So how can we convert it? First, we need to, like whatever the number is, we need to first convert it to a binary form. So for example, if you have 29, like if you want to calculate minus 29, and in 8-bit 2's complement form, then the first bit would be used for sign bit, all right? So we know that. And then we need to have a 7-bit representation for the value of 29. So that would be like 16. And then let me make it correct. So I'll just use a 1101. That's 29. So this is the question. So binary 29 is 11101. And then if we want to get the 2's complement of this 29, that would first one's complement would be 00010. Since we need to have 8-bit, let's add 2 more bits since the value is 2 more bit. The first bit is for sign, so you can note right there. So we have 1011 and then 001. If I invert it, it would be 11000010. So that's the 1's complement, and then the 2's complement would be plus 1. That is 11000011. That's the 2's complement. So from here we can calculate what is the exact number of this binary representation. That's, I guess, 99. 11000011. 11000011. That's 99. Yes. So this is 99, right? So we get the 2's complement form. So how can we write the 2's complement form in binary? So that would be 1 like this. We have minus 29. 2's complement form is this. So the sign bit is 1. So we will have 1 1 0 1 1 1 0 0 0 0 1 1. That's the 2's complement form. Any questions about this?
What was the answer you got again?
So this is the answer. So someone asked 2's complement is infinite entire binary number adding 1. Yes, yes, that's 2's complement. So if it was not negative number, then we wouldn't need the sign bit to be 1. The sign bit would be 0 in the other case. Do we have to have 7 numbers on the beginning? No, it's since it's 8 bit, so you have 7 bits for value and the first bit is for the side. If it's 16 bit, then you have 15 bits value. So the next part is just the opposite. Convert the following 8 bit to 2's complement binary to decimal number. So we will convert the 2's complement again, since we have 8 bit number. So we will take the 7 bits and then make the 2's complement, and from there we'll get the value. So if it's a positive number, the value would not have a minus sign. If this is a negative number, the value should have a negative sign. So let's do one example maybe, then we'll be, I think it'd be better for us. So let's do 1 1 0 1 1 1 0 0. So what is the 2's complement of this binary number? Since we have 2's complement here with 1, that means the negative number. So let's do a 2's complement of 1 1 0 0 0 1 0 0. Then plus 1 would be 0 0 1 0 0 1 0 0. So we have 1 0 0 1 0 0. That number is 36. So this is the representation of minus 36. So this binary representation, the answer is minus 36. Any questions? Okay, so let's move on. How did you know it was negative? Because of the sign bit. Sign bit is 1, that's negative. Sign bit is 0, that's positive. Sign bit is the most significant bit, unless otherwise mentioned. Okay. So next question, trace the behavior of 8-bit parallel row register with something, something, something. So we already did one, so I'll not give like enough detail, just I will just show how to do it. So you need to first draw the rising edges. That way it is easier for you to understand when the transitions will occur. Since there is only one clock and no circle is mentioned about the falling edge, so you don't need to worry about the falling edges here. Just draw the transition point, like wherever the rising edges are. And at that time, you will see some changes in the input. For example, we have I5 here and load is 1 is not present here. So it should not change here, right? As you can see, load 1 should only have the input loaded. That's how the behavior is supposed to be. Clear 1 should clear the input. So the transition should occur after this 1 is here. So in this transition, there should be nothing. So it should be 0, just 0. And then we will have transition here, the first transition. At this point, we have rising edge and load 1, clear 0. That means we can load the data 1 from here. And here in the rising edge, load is 1, clear is 0, data is 124. So the data would be updated to 124 here. The next rising edge, we'll again see if the data needs to be changed. For example, here the data is load is 0, clear is 1. So we will clear the data again. So it would be 0. At the next rising edge, we'll again check it's clear, load is 0. So the data should be again 0. You understand what I'm doing here? Cool, cool. If you have any questions, let me know. I can try to solve that. So whenever there is a rising edge, you need to find out the transition based on the input. So the input specification should be given. Based on that, we can get the output. So that's about the timing diagram of this one. Let's go to the next question. Design an adder that computes sum of 4 8-bit numbers using 8-bit carry ripple adders and calculate the longest time required to compute sum. So I think this is some basic problem. I think that's already covered in the slide. So I'll just follow the slide from the carry adder. Can you go back to 3 really quick? Okay, really quick. About what? Any questions? Let me know if you have any questions. Eric Young. That's it. Okay. Okay. Thank you. Okay. So carry ripple adder. You know the carry ripple adder is just adding the carries in a ripple format. So you need to design this using 4 8-bit number and 8-bit carry ripple adders calculate the longest time required to compute the sum. As your man gets have some delay, blah blah blah. So you need to design this circuit to find out whether this is working properly or not. So how many of you have already done the carry adder, carry ripple adder? Anyone? No? I think this is already given in the like the basics of the carry adder. So you can design an adder by following the truth table. So for example, if we have a 2-bit, this is like total circuit that I have to design if I want to solve this, but I'll just give you some simple examples so you can base your design based on this. So let me see if I can find the solution here. Okay, so let's just do it by ourselves. Then we'll answer for part B of the question reviewed, so we can check our answers. Yes, I can post the answers. Definitely, I can post the answers later, so you can review your design. But I'll need some time to complete this as a whole, because this is something that it will take some time to design. Yeah, so let's do a simple example. Like if we have a 2-bit adder with a carry, then how can we use that? And then we can calculate the longest time required for that, and based on that we can use our design for 8-bit also. So if you have a 2-bit adder, let's say that would require some 2-bit inputs. So our inputs can be 0. Inputs can be A0, A1, B0, B1, and then we have a carry. So it can be 0 0 0 0 0 0 1. So you know, like let's do maybe 1 bit, that way it would be easier. A0, B0, and then we have our output and carry out. So Ci, and then we have the output maybe Y0, and then C0. 0 0 0, and then we will have oops. So on and so forth. Like we can design the truth table from here, and from here we can design the so can you summarize like how would be what would be the kernel map or K map from here? So we need to consider these 3 as the input, and this would be our output. based on that, we can have a k map of eight values, like 3 variables. So maybe c0, a0, v0, and then this one would be for y0. So this would give us an equation for y0. Similarly, we can have an equation for uh, c0, like carry out. This would also be something like similar. So we can get the two equations from here, and based on this we can have our design. And once we have our design, then we can find out how we can get the longest path for the carry ripple adder. So you are allowed to use 8-bit carry ripple adder, so you do not have to worry about implementation of 1-bit and then you serialize version of it, but you can directly use 8-bit adder. So I think the details of it are in one of the slides. I forgot the name of the slide. I have to verify that. There are some circuits given, like the carry ripple adder circuits, so you need to follow those. Can anyone share the name of that file? Maybe circuit that has all the, let's see if I can find that one. Anyways, let's move on to the next problem then. If you have any questions about this, please ask, or we will move to the next part. No questions? Okay. Yeah, I got the circuit. So this one is the carry ripple adder circuit here. Why it's not moving, I don't know. So as you can see, this carry ripple adder flows the carry bit through all the adders. So you will have the longest pipeline based on the number of bits. At every cycle, 1 bit of the carry would be propagated, and one full adder will be required to compute 1 bit only. Based on that, we will have a sum bits and also the carry bits. So you need to get the carry ripple adder used in your design. So using 8-bit, you will have different values based on the propagation delay of all the gates. So this is one full adder, and full adder, I guess, can be implemented with various ways. I guess you can have something like this, adder using a decoder. You can have some simple implementation like this. Based on different things, you can have a different implementation. So I guess this is a full adder. So based on this, you will have your 1-bit calculation. Here there are 4 bits, so extend that for 8-bit and your design should be perfect. Let's move on to the next part.
In this question, if I implement one full adder, and then can I like use like IC for this?
Yes, so you can use that information, and then you have to use the propagation delay for the carry. So the next bit would be computed at the next cycle, right? So you need, if you are using a sequential part, if there is no sequential part, since this is like a combinational circuit, so you just have to calculate the propagation delay and you should be fine.
Okay, thank you.
Any other question? No. Design 4-bit register with 2 control input S0, S1, 4 data input, 4 data output. It means maintain the present value. If it's 0, 0, 0, 1 means load, 1, 0 means clear, 1, 1 means rotate left by 1. So I think it's part of the lab problem. So if you have done the lab problem, then it should be very easy, simple for you. If you haven't done, let me know. I can go through it once again. Does anyone have issue about this problem? Any explanation needed about this problem? Further explanation? Okay, for the previous question, someone asked if one full adder times 8 is 8-bit adder. Yes. So let's just try to draw this one. Maybe if someone has questions about it, so we will be same page. So we need to have 4 D flip-flops to make sure that there are 4 bits information. So we have 4-bit information here with D0 to D1, D3. So let's say this is D0, D1, D2, D3, corresponding to D3, corresponding to 4 bits of the register. And then we will have each bit corresponding one data output. So this would give us Q0, Q1, Q2, and Q3. And then if it's 0, 0, S1 is 0, 0, 0, then it should hold the present value. So we need to have some level of marks to make sure the input of these D flip-flops are connected. So let's say we have 1 marks, let's do 1 bit, and then it will be fine. So these marks have 4 inputs and only 1 outputs based on 2 selector values. So if the selector values are this, S1 is 0. So this would be S1 is 0. So S1 is 0. If that's 0, 0, then this line should be selected and that should hold the previous one. That's it. So the previous value of Q0 should be hold if S1 is 0 is 0, 0. That's what S1 is 0 means hold, maintain the present value. So similarly, S1 is 0, 1 means load. That means we need to have some other input from where we will load. So let's say this is the 1 value. So let's connect it to some input maybe. Let's say I0 input. This I0 input will be given from 1 pin or whatever. So we can get that input from here. So if S1 is 0 is 1, then it will load that value. Again, clear. So we will have a 0 value that should set it to clear. So maybe we can set 0 here for the next bit, 1 0, and 1 1 means rotate left. So by rotate left, we mean if it's something like this and we have the D3 as the MSB and D0 as the LSB, then rotation means like the number is D3, D2, D1, D0. Rotation would be like this. So D3 should be D0. That's why rotate left by 1 bit. So if we have last value here, like the last part 1 1, then D0 should get the value from D3. So this was D3, that would be our D0 if that's rotation. Is that clear? Any confusion about this? Nope. Yes. So if we have 1 bit, then we can extend it to all the other bits and design the circuit overall. And definitely it will need some clock cycle. So I'll have a clock input here, maybe like this. This is our clock. Blah, blah, blah. And that's it. That's the register. So you have to extend it to all the 4 bits and you should be fine. That's question number 5. I'll go to this one. If no one has problem with the register, then we'll go to register 5. Anyone has problem with register? No. I'm assuming no one has problem. So we need to design a 4x8 3-port register file. That's also part of the lab. So we have, I don't think we learned register file yet. Yes, I don't think that's covered in the exam, like the class so far. But in the lab also, we haven't discussed details about register file. So I don't think this will be part of the exam, but you can design it like in a simpler, just give it simple overview, just to give you something. This is a register file has 3 ports here, so to read. So this will be connected to the registers, and then it will have 1 output port, which will also be connected to another register. And then there are 4 into 8. That means we have 4 8-bit register. Is there a topic list that is accurate? Yes, you can follow the problems, practice problems. So that will have, I think, almost details of the register. So this is kind of like the overview of the register file. You read from the registers and then write on the register, write register. So based on this read register, you have two outputs, like where the output register is. See, so this is the read register one, read one, read two, and this is write. And then you will have a read value one. What is the variable value of it? Where, and then read value two. Do you know how many questions will be there? No, I don't know. These last two questions will not be in the exam. Register file will not be in the exam. I can say that safely. Registers, if it's not covered in the class, then it should not be there. Okay, let's move on to the problems of practice problems. So if anyone has any questions about it, then we can share, or not. I'll move on to the next part. So for the practice problem, since there are like many problems, I will not go over like one by one. If you have any questions about any of the problems specifically, then I will try to solve that. If you do not have any problems, I'll just upload all the answers, most of the answers. For example, I have already uploaded chapter 1 solutions, so I'll upload chapter 2, 3, 4, and up to this point. So if you have any specific problems, just let me know so I can solve that. And if you do not have any problem, then I'll just upload all the answers like this. So does anyone have any issues regarding any of these problems? Yes, no.
So you said like doing these problems would be like a good indication of what's going to be on the exam.
Exactly.
Okay.
I think this would be a good practice scenario. Like hopefully this should cover all. This should actually cover all the problems that you have to answer in your exam. But there are like a lot of problems, so I'm not going like all of them one by one. I'll just upload all the answers. Can you go over the last problem on quiz 5? Okay, so I have some questions here. Like, do you know how many questions will be on the exam? No, I cannot. I do not know. Do you know how difficult the sample questions are compared to the actual exam? It will be similar. Can we go over the last problem on quiz 5? Let's go to the last problem on quiz 5. Quiz 5 problems. I think this is the quizzes. Quiz 5. Okay, quiz 5 problem. Preview. So the last problem, this one. You have 8-bit constant given below. What is the constant something? This one. Okay. Write down if constant is less than, equal, or greater than with respect to constant 2. Okay. So 1, that's a constant, and 1 unsigned, that's also a constant. So you know this is a signed representation, this is an unsigned representation, or whatever that representation is. Like here we have unsigned, signed representation is unsigned representation. In both cases they are same, so you should be equal. -1, if you want to write the -1 in 2's complement form, that would have all ones, like it should be 1 1 1 1 1 1, something like that, and that should definitely be greater than this one if we represent it in binary. So in binary, if it's an unsigned comparison, then this would be larger. If it's a signed comparison, this should be smaller. So assuming this is an unsigned comparison, -1 will actually be greater than this one. So if we have a -1 as a signed comparison, which is normal case, like which we can assume, in that case, this -1 would be actually less than 1. For example, here we have unsigned representation of -2. So -2 itself would be very large number because of the binary of 2's complement. So we will have probably 1 1 1 1 1 0 something. So that would be greater than -3 if it's a signed comparison. So you need to understand what is the signed or unsigned comparison. I have some questions here. Let me see what is the question. So we compare the binary representation of constant 1 and constant 2 or the 2's complement of binary representation. It depends on what's given. So if it's, for example, in the last part, like last question, we have unsigned -2. So we need to compare the unsigned value of the binary representation. Like whatever the binary 2's complement representation we have, we compare that with the -3's number. So that would be greater. So -1, if it's compared in an unsigned way, then yes, that would be the correct format. Like 1111 is greater than 0001. But if it's the signed format, then the sign comparison should give you less than. So you need to know what is the sign comparison or unsigned comparison. For example, it's given in the last problem in unsigned -2. So the unsigned representation of -2, that is definitely larger than -3. However, -1 is not larger or greater than -1 unsigned. Is that okay? So what I'm trying to say here is this one shows that you have to first take the 2's complement and then compare it as an unsigned variable. So since it's a minus number and has a 2's complement, so the first bit would be 1, which is a very large number compared to -1, -3. So this should be greater than. Here we have an unsigned number and we have a negative number. So this should be less than, since it's a sign comparison. So you have to find out what is the comparison here. Is it done with sign comparison or unsigned comparison? Any more questions? So someone asked about practice problem 3.59. So let's go to that problem. So what is the 3.59 problem? Chapter 3, 3.59. Design a combination of circuit that compares two 4-bit unsigned numbers A and B to see whether B is greater than A. The circuit has one output X. So X is 1 if A is less than B, and X is 0 if A is greater than equals B. So you have to compare this 4-bit number, right? So you can design the transition table using some basic information. So what we have here is two inputs, A and B, and based on these two inputs, we will have, like, out of four inputs, we will have X as an output only. So since we do not have any detail of the other values, so we can just design it. Get that. So you first need to find out what are the 4 inputs here. So that can be A3, A2, A1, A0. And the other 4 inputs are B3, B2, B1, and B0. And you'll have only one output. So if we have A is less than B, that means we need to find out the relation between these using the, you can either try to draw the state diagram or like the table, or you can use your kind of generalization skill. I think using the truth table would be easier at some point, like when you start to do that. So let's do a simplified version of this using 2 bits, so that way we can extend it further. So let's do A1, A0, and then B1, B0 with an X. So if we have A0 as 0, in this case, X should be 0. 0, 0, 0, 1. Now it would be greater than, right? So it would be 0. Then if we have 0, 0, 1, 0, it's also 0, 0, 0, 1, 1, that's also 0, 0, 1, 0, 0. That's also a huge truth table, like 16 entries. Let's do it anyways. So 0, 1, 0, 0 is 1, and then 0, 1, 0, 1 is 0. It's 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, it's 0. 1, 0, 0, 0 is 1, 1, 0, 0, 1 is 1, 1, 0, 1, 0 is 0, 1, 0, 1, 1 is 0. 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. Oops. So here you can just get the values, and as you can see, if we have a0 and a1 as 0, all the outputs are essentially 0. So you can use that as your generalization purpose. If we have a0 and a1, we have only one output case where we have x equals 1. So since we are trying to find the cases where we have only one scenario, so you can draw a k-map for this, and then from here you can do it, or you can derive the relationship. So for example here, as you can see, if a1 a0 is there, then we don't need to get any of these truth tables, so we can just get these two not, and that should be it, right? Similarly, if we can get a1 a0 to be 0 1, then only one case is true. Here two cases true, here all three cases is true. So you can write down the equation or formula for which we have true cases, and from there you can design the part of the circuit. So if I share the exact solution, it would be similar to something like this. The equation should be, let me see if I can get this correctly or not. It's a big solution, so yeah. What's happening? I don't know. So this is the circuit for input scenario. So they have come up with this generalization: a is less than b if ai is less than bi, and a naught b I naught is equals 1 for all j is less than I. Based on this generalization, they have come up with this equation. So essentially, you need to find that out. What are the generalization that you can make, and based on this generalization, you should be able to save that. So maybe I can clear this truth table for 2. So any questions about this one? Like how can we come to this conclusion? Can we really draw this conclusion or not? Okay. Yeah, so the thing is, like, to solve this problem, sometimes if you just think about having a generalized k-map, or if you try to draw a truth table with 8 bit, that is essentially going to be 2 to the power 8 rows maybe, so which will have like a lot of entries. So sometimes it's easier to just draw generalization if the number of input bits are very large, like this scenario. If it's not the case, if we have the very simple cases like 2 3 inputs and then one output, I think it should be easier for you to just draw the truth table and design correctly. Okay, so any other questions that you need answers? I'll share this answer. I'll try to share the circuit at least for all the answers of the practice problems. I'll upload it in Canvas, so you should be able to verify your design whether that's correct or not. Anything else? Any other question that you want some explanation of? If not, then we will probably end this session. Problem 1 for quiz 5. Okay, problem 1, quiz 5. So let us consider 8 bits. I'll just come back. A sequence of 8 bits can be represented as 2 hexadecimal digit. Okay. Write down the answer in 2's complement of interpreted values in decimal number with the corresponding hexadecimal digits below. For positive numbers, do not put a plus sign, do not insert space after minus. Okay. So if you have A7, then the unsigned representation is directly you can get 10100117. Since the unsigned bit, like the signed bit is 1, so that's a negative number. So the value for 2's complement is you have to get the 2's complement of the 7 bit, and that would be the minus value. So what I'm saying here is you can directly write the unsigned representation at 1010, that's A, and then 0111, that's 7. And value for 2's complement would be just take the 2's complement of this value, since the signing bit is 1. So we get this is a negative number. So get the 2's complement of this value, which would be 0, 0, 0, 1, 1, 0, 1 plus 1, that is 1, 0, 0, 1, 1, 0, 1. The number that is 101, 1001, 89. So this is 89. So the value for 2's complement notation should be minus 89. Do you understand that? So if it's not the MSB is not 1, then we don't need to get the 2's complement. So if we then it won't be a negative number, then it would be a positive number. Then you can get the 2's complement for something else, right? So that's how you can get the value. And looks like all the numbers are negative except for this one, because this one has like 07 FF and all these are like 1, 1, 1, 1, 1, 0 something. So only one number is negative, all the other numbers are positive. Okay, let's clear this. So now if you have any specific problems, you can ask, I can try to answer those problems. If you do not have any specific problems, then we'll probably end this session today. Could you explain what? So I have a question. Could you explain again why you put inputs as they are in the marks in Q5 of sample exam 2? Okay, so sample exam 2, question 5. Why did I put marks? Okay, so we have 4 modes of operation, like S1 is 0 is 0, 0, S1 is 0, 1 does something else, S1 is 0, 1, 0 does something else, and S1 is 0, 1, 1 does something else. So since there are 4 bits of output and we have 4 D flip-flops, we have 4 options to choose from, and then 4 different options will might have 4 different inputs to those D flip-flops. That's why marks is a default choice. You can use something else if you want. You can use probably some decoder also. You can use some other thing. Marks is essentially behaves like some decoder. You can use your own compound logic to do that. But since we have 4 options, like the D flip-flop to hold the previous value, like if we have a D flip-flop here, if we have a D flip-flop, and if we want to hold the previous value, we just have to take the output and connect it, right? So that will hold the previous value, but we should only do that only in case SS is 0, 0. So we can have maybe an AND gate which has this, and then S0 is 0, and then if all of these are something, then we can AND gate won't work, right? So we will need some other combinations. So based on those combinations, we can have the connections corrected properly, but marks would be very simple choice because it's essentially just switches the input here. Does that answer your question? Okay. Any other questions? Anyone?
Can we bring a calculator to class tomorrow and like a scratch paper?
Yes, you can. Yeah, you can bring a calculator for sure. For scratch paper, I think you might need to talk with the professor, like just to make sure that there is nothing written on that. So since professor will be there, I might not be there. So you can use a calculator, but just make sure that you have the paper approved, like whatever paper you're using. Okay. Okay. Any other questions? Will this recording post? Yes, I will post this recording. And I'll also share the circuits for the practice problem. So if you do not have any question, I'll stop recording now. I'll be hanging around maybe 5 more minutes. So if you still have any question that you didn't want to be recorded, this is your time. So the mic is open now.